call will be recorded. So this is exactly, this is during presentation portion of the meeting, and then we'll have a discussion that will not be recorded. So yeah, if you don't wish to be recorded, please turn off your camera and don't speak up. All right, so just to get us started, and while I'm introducing and providing some background information on i2X first, please go ahead to slido.com. We use Slido for discussion and questions as well, but we would like to poll and see who is participating in the meeting. So if you go to slido.com, use first 3 as an event code. And just mark what kind of industry you are representing. It's important to us to understand our audience. So please go ahead and put your vote there. And I'll just continue. So if you are new to the i2X First, this forum is to facilitate understanding and adoption of new and recently updated standards that are relevant for existing and newly interconnecting inverter-based resources such as wind, solar, and storage plants. The forum is convening industry stakeholders to enable practical and harmonized implementation of this new interconnection standards. Yeah, I already mentioned that part of the presentation will be recorded and the discussion will not be recorded. Additionally, the leadership of the team is making a summary document where we include summaries of each meeting, capturing best practices, challenges, and gaps that require future work on each topics. So a little bit about the leadership team. We have Cynthia Bothwell from supporting CETO office, Robert Reedy, supporting CETO office, Will Gorman from Lawrence Berkeley National Lab, Jens Bermer from Electric Power Research Institute, myself, Julia Matevosian from Energy System Integration Group, and Ryan Quinn from Elevate Energy Consulting. All right. So just a summary of the last meeting. The first meeting was just introductory. In the second meeting, we spent on discussing requirements for write-through from IEEE 2800. Standard and also related NERC standard that is currently under development, PRC 29, and how it compares to 2800. MISO presented on their IEEE 2800 adoption efforts, and then we had interactive discussions. And then meeting summary and recording and presentations are all posted, and you can see a link on the slide here. Just to say a few words about key themes at the last meeting. Basically, we were in agreement that adoption of IEEE 2800 is a critical step to ensure reliability of bulk power system with high shares of inverter-based resources, and specifically write-through requirements are of high priority. FERC NERC have generally avoided adoption of IEEE 2800 in their standard development directives and activities. Therefore, it is up to transmission owners, system operators to seek adoption of 2800 in a uniform manner and as uniform as possible. Industry is also strongly encouraged to follow NERC standard development efforts that are following up on FERC Order 901. There is a group of standards that is currently under ballot, and I'll speak about it in a second. There are still inconsistencies between NERC PRC 29 draft and IEEE 2800, and aligning the standards is, of course, very desirable, given that some of the industry already started on the adoption path. Some have already adopted 2800. So any conflicts will be a problem. There are still technical questions pertaining to 2800 write-through clause, as we saw in the last meeting. So we think that continued outreach and education and training is really necessary. And then design evaluation and IEEE 2800 conformity assessment during interconnection process and lifetime of the plant is an essential component of IEEE 2800 requirements implementation, and I'll speak about one step we'll take in that direction in this forum as well. So as I mentioned, we are on the third meeting. The fourth meeting is on August 20th. Depending on how discussion goes today, I believe we'll switch gears towards either reactive power support or frequency support requirements. Below here, you can see the sign-up information for all future meetings for i2X Forum, and then also a link to where you can find posted materials and recordings from previous meetings. Oops, wrong way. All right, so as I mentioned just a minute ago, we would like to do some steps towards talking more about how to ensure conformity assessment with applicable requirements during interconnection process and also throughout the lifetime of the project. And so in that regard, we planned two in-person and online, so hybrid meetings during ESIG fall workshop and during ESIG spring workshop. So the first one is coming up now in October, on Thursday, October 24th, where we'll discuss conformity assessment and specifically cover IBR plant design evaluation process during interconnection, as built evaluation of IBR plant. So basically, if plant as built corresponds to what was studied during interconnection process, and commissioning testing. And we'll specifically try to lift some learnings from the draft of IEEE P2800.2. So high-level agenda for this meeting is already available under link here. As I said, we offer in-person and free online participation options, so you can choose which one you prefer. As I mentioned, meeting is held after ESIG fall workshop, and it will be in Providence, Rhode Island. And at the bottom of the slide, you can see the links to register for in-person one-day meeting and free online meeting. So we'll run both in parallel, and we'll have recording as well. Same as here, recording of presentation sessions will be available after the meeting. All right, just a few words. We discussed, as I mentioned last time, we discussed PRC 29, which is currently being drafted by NERC following up on FERC Order 901. This is the frequency and voltage write-through requirements for inverter-based resources. So draft 2 balloting, I believe that was on when we had our last meeting. It closed on July 8th. Approval rate is relatively low, it's just 35%, and the group received 64 comments from different organizations. Draft 3 was posted just a few days ago on July 22nd, and the ballot is closing on August 12th. As per NERC standards page on this project, this will be the last opportunity for NERC to ballot this project through the traditional mechanism. And then if, if there are issues passing the standard, the board may take requisite actions during the August 2024 meeting to ensure FERC directives are met by November 4th. So basically, if NERC has to submit standards of milestone to FERC by November 4th, and they may take some kind of like non-traditional mechanisms to get the standards through the finish line. And so I linked up the PRC 29 and 2 other standard projects that are relevant for inverter-based resources that are currently in the ballot process. And I encourage you to have a look at those and vote. Of manufacturers to conform with the standards. So we'll hear from 3 manufacturer perspective. So the first one is from Dinesh from T-Mike. This is a solar perspective. Ravi from SMA will provide solar and battery storage perspective, and then Miguel from Vestas will talk about from the perspective of wind turbine manufacturer. And then we'll hear from Jens Bermer from EPRI. EPRI has a similar forum for their members, and there they also conducted this discussion with broader pool of manufacturers, and he'll present a summary of those perspectives as well. We'll have short Q&A, and then we'll have interactive group discussion for about 40 minutes, discussing how the standards may apply to existing resources and also going forward. All right, so without any further ado, just some rules of engagement here. Be respectful, use yes and build on others' ideas, and also we encourage you to speak up or post your questions, but be respectful of others. All right, so we go on to stakeholder presentations, and the first one, I believe, is Dinesh. Dinesh, are you able to share your screen?
Yeah, I can show my screen.
All right. And in the meantime, while Dinesh is sharing his screen, please go ahead to slido.com, use event code first3, and vote the industry that you are representing so that we have a good idea of the makeup of the attendees here. All right, Dinesh, the floor is yours. And could you please briefly introduce yourself as well?
Sure. My name is Dinesh Pattabhiraman. I'm a development engineer here at T-Mic. I work primarily on modeling for power system studies. I work with our customers for meeting interconnection requirements, and I participate in other product development activities here at T-Mic. So this presentation is essentially a T-Mic perspective on the voltage write-through and frequency write-through requirements in Class 7 of IEEE 2800. Just to give you a brief background of our product. So we sell solar inverters, primarily. The inverter that you see on the screen is called the Ninja inverter. We have more than 20 gigawatts of this inverter shipped in North America, and so this is essentially the inverter we'll be talking about in terms of write-through requirements and so on. So from a OEM perspective, while there are standards such as 2800 and NUC PRC, as an OEM, we are primarily focused on meeting UL requirements as certification requirements. And certification requirements include compliance to certain write-through and protection functions. In North America, UL listing is very important, and UL certification process is taken very seriously as an OEM at T-Mic. So for most of our existing inverters in the field, we meet UL 1741 requirements, especially the supplement A portion. It's referred to as SA. And typically to meet NUC requirements or ISO requirements, we add additional software related to what the UL standard requires us to meet. Often the UL 1741 standard is based on distributed energy resources, the DER standard for distributed generation. And it has a certain requirement for write-through curves, frequency write-through, and so on. The old standard required us to do momentarization, which is not acceptable for NUG or ISO requirements. So we incorporate additional software to eliminate momentarization and perform other things like reactive current injection, extend voltage and phase angle write-through capability. Moving forward, the last year or so, the next version of the UL 1741 standard has been adopted by the industry. So we now have compliance to UL 1741 SB, and we have our inverters certified to this new standard, which requires certain modifications in firmware as well as hardware, but our next generation, essentially inverter, is compliant to this 1741 SB standard. The reason I'm telling you about all this is because we view UL 1741 SB as a major step in meeting 2800 requirements. A lot of requirements in this SB standard are synonymous with 2800, not necessarily the same, but on a very similar line. And often, when we put these standards on the same level, certain numbers are slightly different. So when we do our certification test, we try to meet the higher requirement compared to either SB or 2800. Some samples are shown here. For example, rate of change of frequency right through in class 7.3 requires about 5 hertz per second of right through in IEEE 2800, whereas in 7041 SB we have about 3 hertz per second requirement. So when we tested for the 5 hertz per second requirement, and for phase change right through we tested for 25 degrees as required by 2800 instead of 20 degrees. One thing to note is that 2800 works at a plant level. It doesn't work at an inverter level. The 1741 certification is an inverter level certification. So we test these requirements at the inverter level, not necessarily at a plant level. And these are all tests performed in the lab under certain conditions. So the testing procedure for 2800 might be actually different from 1741 SB. That would depend on 2800.2. That would come in later. Other similar requirements, we have voltage right-through curves. In general, the right-through curve is slightly wider in SB for most right-through scenarios, but certain portions of the curve are wider in 2800. But we generally think that our 7041 SB inverter would be able to meet the requirements in 2800 as well. Similar thing with consecutive voltage right-through. So the right-through specification in 2800 talks about a certain number of events per certain time durations, whereas SB has a very different definition of consecutive right-through. But based on our understanding, we think that the SB requirement is probably a little more stringent than the 2800 requirement. So, and also our inverters are not actively monitored for consecutive disturbances. So we believe that we would be able to meet that portion as well with the SB certified inverter. So in terms of reactive current injection during right through, most of our inverters can do reactive injection today. In fact, this is required by almost every ISO that we know of today, requiring reactive injection during grid events or fault events essentially. The standard specifies the default injection mode to be reactive power priority. So our inverters by default operate in reactive current priority during these fault right-through events. So that portion of the standard we would be able to meet. But the standard also specifies that you would need the ability to choose between active current priority and reactive current priority. We don't have that feature available today. We would have to wait for some ISO requirements to see what the ISO specifically wants during fault events. For example, ERCOT prefers reactive injection during fault events. CAISO has a very specific statement that they need a certain level of reactive injection during fault events. So we don't see this being widely adopted by ISO. So reactive injection is always being prioritized. While it is a software change that we can implement, we think that most people would be using reactive injection. When it is required by certain ISOs, we would be developing that function, but we don't have that available today. Negative sequence injection, today we don't have any requirements that we see from anybody requiring negative sequence current injection on the grid. Most, at least to our best knowledge, most inverters today inject only positive sequence current during fault events. We do have certain negative sequence injection capability, but we do not enable it for our US market. So we are definitely concerned about how this function, if enabled, can affect inverter performance during right-through event, and we don't have extensive experience of studies with this function, power system studies with this function. So currently we are not enabling this. So we would wait for more guidance from ISOs on how to study this and how to test this, and how this is going to be beneficial to their system. And we're kind of waiting on that portion to be discussed by ISO requirements. Response time and accuracy, there are accuracy requirements, I think plus 10% and minus 2.5%, as well as a time requirement for these functions within, I think, 2.5 cycles to 4 cycles for steady state. So we believe we can meet these requirements today with our existing inverters, even in the field. We don't have any problems in that regard on existing inverters or new inverters. So whatever I'm talking about current injection applies to both most of our existing inverters in the field as well as newer inverters. So transient overvoltage right through, this is again something that is very hard to judge from an inverter unit perspective. This is not really covered by an SB standard in terms of inverter level requirements. This is often dependent very significantly on the plant itself, because a plant construction can include several components like surge resistors or even the collector system equivalents that can affect transient overvoltage right through capabilities. So this depends on the design of the plant as well. So at an inverter level, we don't have any tests that are available right now to kind of study and meet this part of the standard. We're waiting for 2800.2, the test procedures from the final standard. So we did some internal studies to see if the inverter can write through with certain protection functions. We were able to see that it is possible to write through with appropriate protection settings, but again, we cannot say for sure until we have more guidance on this. The last part of this presentation, a couple of slides, are not related to 2800, but kind of a perspective from T-Mike experience on write-through events or grid events in the field. So a lot of people view 2800, essentially it's an industry-wide effort to kind of push towards 2800, at least for newer sites, and even adopt certain aspects of 2800 for old inverters. While we think that is useful, there are also certain things that people should understand that just moving towards 2800 is not going to be able to improve the write-through capability of all inverters. There is a lot of focus on voltage write-through requirements in 2800. Based on our experience, we had inverters tripped during grid events in ERCOT and other locations. None of our inverter trips have actually exceeded any of the voltage write-through curves specified, even in PRC24. The curve in PRC24 is narrower than 2800, and none of the events even came close to any of these curves. Most of the events that occurred in the field that caused inverter trips are 3-cycle, 4-cycle fault events. And a lot of these issues come from the old perspective of inverters not doing any harm in the grid and meeting the age-old saying of like, do not do any harm, just get off the grid as soon as possible. So the inverters have come a long way since that, and they've the protection functions have changed over time to meet transmission requirements. The understanding among inverter OEMs, at least from a T-Mike perspective, has changed. So in many cases, what we found is that, at least in some cases, some grid requirements have actually caused inverters to trip more than they would have. So in some cases, some ISO specify very aggressive reactive injection requirements, based on studies that were performed a long back without actual clear evidence of how they would pose an improvement to the power system. But these aggressive injection functions have kind of caused inverters to overvoltage and trip under certain scenarios during weak system events. So in some cases, the requirements can actually push the inverters to trip themselves. So there needs to be an increased understanding of how these functions are to be programmed, what the trade-offs are, and they're not really discussed in 2800. So some guidelines here for improving performance, it doesn't mean you have to go towards 2800, but there's certainly things you could do that would improve the inverter performance. And the first thing that you would have to do is just make sure you do an EMT study of the plant and ensure that the settings of inverters in the field match the actual EMT study performed. In a lot of cases, we see that EMT studies are performed, and if it is checked off the list, the model is not really used in. When we get to the field, we do not actually get feedback on what settings need to be programmed on the inverters. So we often hear that, we can program whatever we want to some extent, because the study that was done, the model is, there's a check off on the list of things that need to be done, and the model is often lost. So one thing that moving forward is needed is essentially to match EMT studies with the plan. And this is already happening in places like ERCOT, where there is a model verification report required now to match plan settings. And hopefully this improves the performance during grid events, because we have seen that, if the studies don't match, the protection settings on the inverters don't really reflect, or the parameters in the inverter don't reflect EMT studies. And they have certainly caused a couple of trip events in our experience. So other thing to do would be to consult the OEM on best possible settings, to confirm with the OEM on how each protection setting works in the inverter, and make sure their recommendations are taken into effect when tuning the model performance for the plant as well. It is also important to study the past grid events and consult with the appropriate OEM on what model settings can improve inverter performance, and how whether the OEM has a mitigation strategy for events that were experienced in the past. So these are essentially just a few suggestions that don't relate to 2800, but are very key to how inverters perform in the field. I think that's it for my presentation. So.
Right. Thank you, Dinesh. And yeah, thanks for keeping the time. There are some questions on Slido. So you can go ahead and have a look. Maybe you can answer some of them already while others are talking.
Sure.
We'll go to, and we'll have Q&A at the end of all three presentations as well. We'll now go to Ravi from SMA to present the OEM perspective. Ravi, please try sharing your screen if you can.
Yes, I will.
While Ravi is sharing, just a reminder to go to slido.com, and there is a polling question there to vote for industry that you are representing. We have 68 responses now and 192 people on the call. So please indicate where you're from. It helps us to prepare future meetings as well. Go ahead, Ravi.
Right. Can you see my screen?
Yes.
And you can hear me?
Yes. And
Excellent.
could you please introduce yourself briefly as well?
Yes. I'm Ravi Dodbalapur from SMA America. I'm the Senior Director for Applications Engineering. My counterpart is Scott Carpeel. He is out camping in Colorado. He is the subject matter expert on IEEE 2800 at SMA US. We collaborate a lot with our headquarters in Germany. And Scott's the principal applications engineer. He would be presenting in this forum, but since he's camping, I'm doing it on his behalf. So just the normal disclaimer that our lawyers make us do. No guarantee of any accuracy of information. I'm kidding, but it's the disclaimer. IEEE 2800 readiness. SMA's perspective on this is the previous standards dealt with voltage right through, frequency right through, grid disturbances, and IEEE 2800 is now there is a definition of exactly what the inverter behavior should look like, or what the options are while the inverter is in right through. There is the limits on voltage, on frequency, return to service, and all of that. Most of that is consistent with the IEEE 1547 standards, the UL 1741, SASB standards, just like Dinesh said. The augmentation in the IEEE 2800 is now there is a further definition of exactly what the inverter behavior should be for during a fault write-through event. So looking at the major sections of the subsections under section 7, you have the voltage write-through and protection requirements. Those are met by SMA equipment now. So no enhancements are needed in the equipment. Voltage disturbance write-through, this is where we have a little bit of warning, just like the next mentioned. I think these have to be confirmed for grid strength and various other conditions during an EMT study. Confirmation needs to be required to conform to voltage disturbance requirements under section 7.2.2, and I have a further slide kind of explaining that. Transient over voltage write-through requirement is new. The earlier requirement in IEEE 1547 was more about load rejection write-through. The emphasis was more on the inverter not causing an overvoltage. Here it is about grid events happen, capacitor switching events happen, fault clearing events happen, a transient overvoltage happens. A lot of inverters trip under these conditions. And typically it is not the inverter that is the problem. It's typically the auxiliary equipment, the power supplies, the cooling fans that really need to be protected from transient overvoltages. So at SMA, we have a option that adds a transient overvoltage suppression device to all of the auxiliaries. And with that option selected, we meet the transient overvoltage write-through requirement. The frequency trip requirements in section 7.3 haven't really changed that much. Our present products and future products will all meet the frequency trip requirements. Same's the case with frequency disturbance. Typically, frequency is not generally the problem for inverter behavior. So 7.3.2 section is also fairly easily met. And then the return to service section 7.4, again, SMA can comply to those requirements. Rokoff of 5 Hertz per second is met with appropriate parameter settings. And Dinesh mentioned this too. The earlier IEEE 1547 requirements of anti-islanding protection made the parameters rather sensitive to Rokoff. But if you are turning off anti-island protection on these transmission connected projects, we can open up the Rokoff settings. The 5 Hertz per second is quite easily met. Phase jump right through 25 degrees is the requirement in the standard. In our hardware in the loop system, we have tested our equipment up to 60 degrees. And fault recording as a feature has been in SMA equipment for a long time. This is high resolution data. It's almost like having a scope inside the inverter. It captures switching frequency information, DC side information, AC side information, voltage, current, frequency, commands that are going in the inverter. If there are trip signals coming from hardware, software, all of that gets captured pre-fault, during the fault, and post-fault. So we've had this fault recording feature in our inverters for almost 3 generations of inverters. Coming to the section 7.2.2, which is the voltage disturbance right-through section, which is where confirmation through EMT modeling is definitely recommended. The voltage disturbance section for continuous operation, that's can be generally met. It is the mandatory operation during low voltage and high voltage right through for certain conditions where the table 13 requirements of 4 cycle settling time, minus 2.5% to 10% settling band for all conditions needs to be confirmed. When you have a low short circuit ratio at the point of interconnection point POC, these adjustments will need to be made on a plant-wide basis. So EMT, PSCAD type simulation would bring that condition to bear, and appropriate parameter settings would need to be made to meet these mandatory operation conditions. Consecutive voltage, Dinesh mentioned, this is not something that the inverter really gets affected by. However, the type of fault that can happen consecutively does play a part. Again, the excursion of the voltage from nominal, as well as the short circuit ratio availability at the point of POC will all play a part. These need to be confirmed on a project-wise basis through modeling, PSCAD, EMT type modeling. Dynamic voltage support, again, this we generally can meet, shouldn't be a problem. And then a restore output after a voltage right-through event, we can generally meet. Summarizing SMA's readiness for IEEE 2800, we can generally confirm that our current products will meet the requirements for all new installs. Just have to select the right options in the hardware and set the correct parameters in the firmware. So if you have a properly configured inverter setup, then our current products definitely, we feel very confident, will meet the IEEE 2800 requirements. On our installed base, some upgrades are needed, like the transient over voltage right through requirement, which is new. That's a hardware upgrade that has to happen for if that option was not pre-selected, and firmware updates and parameter adjustments have to be made for our installed base. We are 4 generations into our inverter products in the US, and our pre-2015 products, which is the CP series of products, that is under review in R&D. But post 2015, our megawatt sized inverters can all meet IEEE 2800 requirements. And the way we intend to comply is through a self-declaration for IEEE 2800 till such time that the test standard being developed in IEEE 2800.2 is fully completed. Questions?
Thank you, Ravi. We'll take questions at the end, but feel free to look at the slido.com and event code first 3. We have some questions there in Q&A. I have enabled ability for people to reply, so feel free to reply some of the questions there. All right, we'll move on to Miguel. Miguel Acosta from Vestas. Miguel, you ready?
Yeah, I think Miguel is not a co-host, so I think he would need to be a co-host to unmute himself. But Dexter could probably unmute him.
Yeah, he's all good. I made a different Miguel a co-host, but I just made Miguel Vestas a co-host, so you should be good to go.
Yeah, I think he signed in twice because he's having some issues with audio.
All good. He should be all good. Are you okay, Miguel?
Still cannot hear.
Can you hear me?
Oh, yes, great. We can hear you.
No, but if you can unmute my other account, I need to be, if possible, unmute presented in one and unmute in the other one. I have some audio issues.
No problem. You are co-host in both, so you can unmute yourself.
Okay, just checking. Can you hear me?
Yeah, you'll need to mute one of those because there's an echo.
Now it's better.
Perfect. Thank you.
Okie dokie.
All right. While Miguel is sharing his screen, just one reminder again to go to slido.com, code first 3. And there you can vote on a live poll to say what industry you're from. We still just have half of people indicate that. And then you can post your question in the Q&A window. I've also shared in the chat here and in the Slido a link to where materials are posted after the meeting. And you can find materials from all previous meetings. People were asking about that as well. All right, Miguel, go ahead and introduce yourself, please.
Great. Thank you, Julia. I hope you can hear me and you can see my screen.
Loud and clear.
Great. My name is Miguel Acosta. I'm a senior specialist in the power plant solutions, working for Vestas from US, looking into grid compliance and in both Canada and USA. And today's presentation will be focused my other two colleagues on the class 7 of the IEEE, but more than showing some results and a bunch of green checks on each class, I would like to discuss some of the key issues on the IEEE 2800 and how we should, in our perspective, determine if the plans are compliant or not. So I will start with a very basic slide that I have presented in the past. That is what is known. We know that we have 12 clauses in IEEE 2800. 10 of them are mainly about grid compliance and modeling. I kept some of the data retention and other stuff outside this known part. But if we look at the compliance, we have seen that a lot of new requirements are proposed to be introduced, especially class 7, that is the most let's say, that's creating more noise in the industry. and it's being partially implemented by some TSOs. And yeah, so I would like to emphasize what is really unknown. And I don't know if you keep seeing my Teams meeting popping up. I hope not. Yeah, you can see it. Anyway,
now it's just
yeah. So in the unknown part, which is very important to keep in mind, is all the compliance evidence, testing procedures, actually verification, type test, and exemption process. There are a lot of pending topics to be discussed and agreed in the industry that requires further clarification to understand if we can really put a green check mark next to each of the sub-bullets in the clause 7, and actually in all the clauses. So the point of this presentation will be to pay attention, because the devil is in the details, and we might determine something is compliant when it's not, and the opposite. So we might get false positives or false negatives in many occasions. How to demonstrate IEEE 2800 compliance is something that's still under discussion. We have 2800.2 with 5 different sub-working groups where we are defining what should be the criteria. But this slide shows more or less the different kinds of options we have to determine compliance. We have all the way from field test to request an exemption for a specific requirement. It's very important this, because we might hear sometimes some OEM saying, okay, we can demonstrate this by issuing a statement. Some other ISOs might require that you simulate this into an EMT, which might be impossible. And we have seen that multiple times in industry presentations. So it's very important to have a consensus in the industry how we will verify each of those clauses, just to make sure the purpose here is not to have evidence if something goes wrong, that we can determine who is guilty in case there is an issue in the grid. The case here is to have a common understanding and enhance the generation to their best of their capabilities, either if it's by field test, simulations, how we're in the loop, or during commissioning. That's not really important. The important is that we all have a common ground of what is needed for each of the clauses to be verified. Now, this is, I think, key when evaluating the 2800 compliance. I will show later on in this presentation a table with check marks, of course, similar to the one presented by my colleague from SMA, but that really depends. And I will show you how it depends and how those greens can turn into yellow or even red if we test things in one way or another. So when we're talking about IEEE 2800 compliance as an OEM in US, we receive multiple customers asking, Vestas, how are you prepared for IEEE 2800? And then we receive another group of ISOs reaching out, trying to evaluate or issuing RFIs to understand how our technology is prepared for the IEEE 2800. And we know some things. We know the upper part of the iceberg, but we don't know many things on how those things will be tested. And also we know, and I think someone mentioned it in the previous presentation, that all those things are project specific, right? So it's not the same to evaluate in the Park A or Park B. So the grid stiffness, the PPC configuration, the weighted short circuit ratio of nearby IBR plants, all that depends on the same criteria, might fail in one plant and might pass in another plant. But we are in this, what I call here the three-way catch, that ISOs are constantly asking the generator owners, and the generator owner says, well, I don't know the capabilities of the turbine. And here turbine could be a solar, right? I don't know, I just know the BOP, but I don't have a full understanding of the turbines. When the ISO asks, okay, what are the capabilities, what turbines can do? We as an OEM say, I cannot guarantee a specific plant will ride through. I don't know how the BOP, I don't know what transformer they have, what control strategy they have chosen. There are many question marks for us when we see as a project the compliance of IEEE 2800. And at the end, from the ISO perspective, They don't really care because they want to protect the grid and eventually enforce those requirements dictated or suggested by the IEEE 2800. So from the ISO perspective, it's two question marks that needs to be resolved between the GO and the OEM. So this is very important when we are evaluating this. And until we don't have a very detailed criteria, step by step, in how to evaluate IEEE 2800 in different manners, from commissioning to simulations or statements from OEMs, it will be very, very difficult to do what I'm doing in the next slide. It will be very difficult to put a yes or no. So that's why instead of putting yes and no's, I have put high and lows and some mediums. So this is the likelihood that we will be compliant to some of the clauses that are in here. As you can see, I have put 5, 6, and 7, but this time I will focus on the right-hand side of this slide and just go through some of the sections in the abnormal condition section. I think most of the ones not highlighted but circulated in red have been discussed by my colleagues. So I will focus on the LVRT performance, that where my cursor is right now. I don't know if you can see my cursor, but the 72233, then the consecutive voltage deviation, or the multiple FRT, how it's called in some other places in the world, the transient over voltage, which is very important, and finally the rock off. So looking at the consecutive voltage ride through, this is very dependent on the technology we are evaluating. It's not the same to evaluate a type 4 machine or a solar than a type 3 machine, where the mechanics are really involved. But besides those differences, what is really important is to understand that the multiple FRT is something that, of course, it might happen in the grid, but also depends on how you configure your plant. It's very important to keep that in mind, because in an ideal world, when there is no special configurations to the plant that you are evaluating, you might have one result. But if you decide to configure the same plant in a different way, you might fail the same criteria. So that's why it's very important to keep in mind those should be project specific. One thing that we are seeing in the industry is that some ISOs are suggesting some tests to run in EMT simulation or RMS simulation, doesn't matter, to evaluate this. And we have to keep that in mind when we are doing this, because the reality is that most of the models out there, they do not contain a proper thermal model for the chopper or whatever the technology is that dissipates the energy from the resource to the grid. So if you don't have an accurate model of your energy dissipation, you cannot monitor the temperature, which is the weak point when you have multiple FRT. Having said that, if I test this in a generic model, I will write through 1 million faults, because the first fault will be identical to the fault 100 or 1 million, as long as there are no grid instabilities in voltage. But my weaker point from an OEM design perspective, that is the thermal part, is not being considered. So what if I include the thermal model? Well, that's also tricky, because if we include the thermal model, you can see a comparison between left and right in here, that in some occasions, you might be compliant on the left-hand side when I'm operating in a very strong grid, because I can recover the power very, very fast. And the yellow shaded area is very small. So the chopper is burning energy during a very short period compared to the duration of the fault. However, if I try to slow down that recovery phase and then I recover slowly, then the chopper is actually being stressed significantly while the turbine is recovering. So the right-hand side, that is a project-specific configuration, might fail the same clock that a strong grid, that a project connected into a strong grid will pass. So it's very important the how and the how to define it, and the project specifics. Another, sorry, I'm really sorry that I cannot unmute my team.
No worries, that's something.
Give me just a second, please. I will try to quit Teams. Okay. Okay, I hope now it's working. So another important point is the clause 7324 is another of the clause that is creating some noise in the industry, and it's about the phase jump. Fortunately, for a type 4 machine that is our main technology, a phase jump is relatively straightforward when you don't have a direct couple induction generator like a type 3 machine. Our main technology is the type 4 machine, so we can easily ride through the phase jump of 25 degrees. However, it's really important to keep in mind that the PLL is also configured to the specifics of the plant. That means that every plant will not have the same KPs and KIs on the PI of a PLL, so they will react differently to the same phase jump. So some of them will reach certain frequency or certain voltage that the other plant will not reach with the same technology, simply because it's configured in a different way. In the next slide, I try to illustrate how the same PLL will also react differently depending on the grid strength. So the same PLL could also react differently, configured in the exact same way if the grid strength is different. So this is important to keep in mind, because there is a fake conception that some of the OEM technologies have some sort of protection that is monitoring phase jump, and that's not true. At least for Vestas, there is no such thing as a phase jump protection where you can put a number and then you trip for certain degree phase jump. You only monitor the outputs of the PLL when you are performing DQ control, and the outputs of the PLL are basically the voltage and the frequency. So the protections that will actually cause the turbine to trip when there is a phase jump are the voltage protection and the frequency protection, and they are just a consequence of the phase jump. So that's also very important to keep in mind. And this again here about the devil is in the details, right? What exactly am I testing? Am I following ERCOT MQT when there is an SMIB? Or am I actually considering the full plant model? Am I testing in the way that, for example, some ISOs require that is in a generic plan, or I'm using the site specifics of my plan? Those details are very important. So just a takeaway here of the PLL performance, this is more for documentation. Some of the constants that regulate the PI control of the PLL will have a direct impact on the voltage and frequency, and also the grid strength. So it's very important to define the way we have to monitor this in future. So these two are very good examples that sometimes the greater good is necessary, and there might be cases where we need exemptions. We might need to reduce, in some cases, the multiple FRT number that we can write through, as long as we can recover voltage in a stable manner. But we might not evaluate that same plant in the same way. Same happens with the voltage phase jump and the control stability. We might have to tune a PLL in a very specific way when there is a very weak grid to reduce the constants of that PI controller and maintain the voltage stability, but we might not ride through the 25 degrees. So it's a trade-off that is very important to keep in mind between the project specifics and the actual product capability. How much time do I have left, Julia? Because I have
But
to
you can
restart
take a
it.
couple of minutes.
Okay, I have okay. Another important clause that I wanted to introduce here was the rock-off, because we are seeing also a lot of debate in the industry in terms of how to evaluate that half of a page section that is included in the IEEE 2800. We all know what ROCOF means, but there is no agreement in the industry on how the ROCOF should be measured in real life. And on top of that, we don't know exactly yet how to apply these criteria into the actual technology of the OEM. I will give you a very simple example. When we evaluate ROCOF in a lab containing an actual hardware in the loop, we can pass huge amounts of ROCOF in the 2-digit level. But when you actually evaluate the same ROCOF in the field, you will realize the turbines will trip. And they will trip, and I think someone mentioned it before me, because some of the auxiliary services needs to be considered. So those auxiliary services might trip due to ROCOF, but your converter will not. So we are here in a dilemma that, okay, ROCOF, similar to phase jump, is not a value that I put in the turbine and say, I ride through 6 or ride through 5. No. The converter, similar to the PLL, will produce some certain frequency. And when that frequency is outside the clause 732, that is the disturbance right through requirement, the normal operation, then you eventually will trip. So if we can withstand 6% in our technology, 6% is 3.6 hertz. So as long as that ROCOF doesn't reach 3.6 hertz, so if it's at a rate of 5 hertz per second, it will reach 5 hertz extra in 1 full second. So it will be around 0.68 seconds that will reach that. So it's very important to understand the way we are going to evaluate the ROCOF. If we evaluate ROCOF on a converter level, we might get a false positive that we can write through when in comparison, if we evaluate it on the field. And on top of this, to add some more complexity, we say it's very difficult, near to impossible, to create an event that can evaluate ROCOF on the field. So we might rely on simulations, but the reality is that the simulation models do not contain auxiliary systems. So, or most of the simulation models do not contain the auxiliary systems. So if I test ROCOF in a PSCAD model that I have the impression that is super accurate, might not give me the reality of what the ROCOF capabilities of the technology are. Finally, some thoughts and suggestions about this is that one of them is very important, and that we have unification and standardization in the criteria, and that's why it's very important to wait for the outcome of the IEEE 2800.2, because we would like to avoid a case where we have multiple ISOs in the US and Canada evaluating the same requirement from a different perspective. We have seen some proposal. ERCOT is the front runner in evaluating this with NOVA 245, NOVA 255 for data retention. So we have seen how much debate there is, and the different understanding between different people in the industry, and the same requirement, the exact same requirement in the 2800 can be interpreted in different manners, and we might reach some unrealistic way of testing or evaluating that. So it's very important to monitor the 2800.2 and have a common understanding on how that should be applied in the industry and in the field. Also very important to keep in mind that there will be site-specific configuration of some plants that we need to look at the greater good, and we might have to supersede or create some sort of exemption for the 2800. And the last bullet point that I think is partially in the discussion, Julia, but I wouldn't like to finish before closing with this point, is the retrofit and repower of the wind farm. We have out there technology that will be retired in 5-10 years, that in some areas IEEE 2800 will not be applicable retroactively, right? If it's not applicable retroactively, in theory, those facilities with still 5-10 years of lifetime, they don't have to be compliant. But we are facing the situation where we might have to repower those to a technology that is not the latest, that can do better in terms of grid compliance, but cannot reach the IEEE 2800. ERCOT in the NOVO 245 have introduced this exemption, they have granted some sort of exemption considering retrofit and repower projects until 2028. So any project that is in operation and will be retrofit or repower will not be subject to NOVO 245, which is IEEE 2800 in basically. So we should think about this as well for the rest of the ISOs in US. Retrofit and repower projects should have some sort of different requirements or exemption because they are improving for better. They might not reach the super high bar, but they are increasing their capability. So it will be, in my opinion, unfair to ask that much. If they can do a little bit less, they will be doing a greater good for the grid in comparison if you leave the very old and obsolete technology that will be retired in a couple of years. So that's something that I would like to add in the discussion phase, Julia, if possible. But you are the boss. So
definitely, thanks, Miguel. We'll bring it up. We have a question on application of these requirements to legacy plants as well. We'll talk about that. All right. So last but not least, we have Jens from EPRI to kind of present a summary of perspectives that they heard in similar EPRI's forums. And your slides are up, Jens, but I cannot hear you yet.
I think Jens also needs to be a co-host. Yeah.
Jens, you should be able to unmute yourself now.
Yeah, thank you so much. Thank you for the previous presenters, and thank you, Julia, for having us here today. I would like to also thank my colleague Manish Patel, who has helped with this summary here. Before we jump into some of the details, I just wanted to recall some of the terminology we've been using in the industry and how we should really be very intentional about whether we talk about compliance or conformity or compatibility. So I think today we've really focused on compatibility, which is the question of whether a given equipment is designed to support the conformity of or the compliance of a more complex system, for example, the IVR plant. And I think each of those OEMs here today stressed the importance of not mistaking inverter unit compatibility with plant level conformity or even compliance. Conformity, on the other hand, is adherence to certain voluntary industry standards or procedures. So that could be IEEE 2800.2 once it's published, whereas then compliance is really meeting mandatory legal and regulatory obligations, including, for example, the NERC reliability standards. So they are very distinct uses of the language, and it's very important that for today we focus on the compatibility issue related to the inverter technology. So this is just a very kind of higher level summary of some example challenges that we have become aware on EPRI side related to requirements in 2800, specifically for the three technologies that were also represented here today. So I'm not going to go into the detail given the time, it's short, but I think we do need to acknowledge that, first of all, the requirements are at plant level, and that does not necessarily immediately translate to what is needed for compatibility at the unit level. We also need to acknowledge that some of the requirements in
discussion.
Sorry, maybe mute. Miguel. We need to acknowledge that some of the requirements in 2800 are still somewhat vague. So we heard from some of the OEMs how they are interpreted differently by different people. And as we all learn together how to adopt and apply 2800, hopefully we will at least move towards a joint interpretation of these requirements. And future revisions of this first edition of the standard can also help in that. And then last not least, how to actually utilize some of those requirements are also not, is not specified in the standard. That might relate to some future application guidance that could be needed. So in terms of looking at the overview of requirements in the standard, and I believe you may have seen this slide before. With right now on this slide, we're looking at legacy units, and the colors show which areas seem to be more challenging with some concerns than others. So focusing on the write-through, it's really the unbalanced current injection, which we heard from at least one OEM today that they may not be able to do that just yet, and certainly not for legacy units, but also transient over voltage and consecutive voltage write-through, as well as to some extent maybe the row-off and phase jump requirements. Now, when we look at the new IBR units, then the picture looks a little bit more optimistic. We do expect most of the new and compatible 2800 inverters to be capable of injecting unbalanced current injection during the fault. But there are still some challenges related to the transient over voltage and the consecutive voltage write-through, as we heard today, and some related to row-off or phase angle jump write-through. Now, today, we're focusing on the write-through only, and just to summarize and keep this brief, I'm going to give you a bit more detail on the transient over voltage and consecutive write-through challenges. And part of that is probably somewhat repetitive to what you've heard. But really the takeaways here is that for transient over voltage write-through requirement, this is a planned level requirement. So the plant is allowed to trip based on transient over voltage for if the transient over voltage is above the specified thresholds for a certain duration or longer, even if the RMS voltage is within the mandatory or continuous operation region. So it's all about the time frame. Now, typically for transient over voltage, if you use protection, then that protection is not applied at the point of measurement, but it is applied at the point of connection, which are the IBR unit terminals, in order to protect the inverters from damage. That said, throughout the plant, you might use surge arresters or other means in order to coordinate some of the transient over voltage. And therefore, the protection applied at the unit level needs to be coordinated with other elements throughout the plant. It is also important to understand how a transient over voltage at the POM would translate to transient over voltages at the POC. If you do have surge arresters or similar things in the plant, some of them may clip parts of that over voltage. So you do not necessarily have to set your IBR unit transient over voltage protection at the highest value of what's specified in IEEE 2800. We have tested some inverters and know that they are capable of riding through transient over voltage up to 1.5 per unit, for example. Some of the challenges, however, and you heard that before, is that one would need a non-aggregated EMT model to really study the transient over voltage exposure of the units in the plant, and the measurements would have to be taken at the plant and the unit level. And the equipment for those high resolution measurements in the transit time frame might be limited, or at least come with some specific costs. So the whole question of conformity assessment of the plant without adequate measurements can be a challenge. And last, the coordination between the IBR units, application of proper surge protection within the plant is really a very specific design question, which the engineers working for developers or the engineering departments within developers have to have the capability to design all of that and coordinate appropriately. So it is very much a design step requirement. Now, on the other hand, consecutive voltage deviation rights capability, and this is what Miguel already summarized here, is quite complicated, actually, as defined in the standard. So a future revision of this very first edition of the standard could potentially improve that section further. And we also would like to highlight the fact that the requirement includes an exception for isolated IBRs that connect via VSC HVDC due to the limitation of the DC chopper to absorb the energy. And 2800 includes an annex in which a full rated power output over 2 seconds is considered one possible design criteria for VSC HVDC. And I think with that, I'm done with my brief summary, but I'll be happy to expand on any questions that may arise. Thank you, Julia.
All right, thanks so much, Jens. Okay, so we'll go to Q&A, and Dexter, maybe you can stop the recording now. So